Hi everyone. So today we are tackling one of the most important topics in hydraulic engineering, open channel flow and culvert design. We have four problems today, and I will go through in them in details. So our first problem is related to gradually varied flow, and we can solve that using the two approach like direct step and standard step method as well. And our problems first problem is we have a rectangular channel of 400 cfs, 10 feet wide, and slope of 0.0018 and Manning's and at 0.018. At one section, the depth is 4.5 feet, whereas in another depth that is downstream, it is 4.7 feet. And the question asks us to determine the distance between those two depths. So it is a classic gradually varied flow problems, and the depth is changing gradually along the channel, and we need to find the distance over which the change happens. We will use two steps here, like finding one is direct step method and another one is standard step method, which involves calculation in Excel or some other computer programs. So for the first direct step methods, that is for rectangular channel. So since all these are given values, since all these are given parameters that I have written here, and second thing, we need to compute the specific energy at both section, and our specific energy formula is given as y plus b squared divided by 2g, and at upstream, our area will be equal to 45 feet square, whereas B1 it will be equal to 8.89 feet. So when we compute this area and velocity, we can directly input in the upstream energy, specific energy, and we can compute that as 5.73. Similarly, for downstream area and velocity, we can do the same process since we already know the y2, y1, all those values. So we just input in the formula, and we have area 2 as 47 feet square, and velocity 2 as 8.51 feet, and we use the same formula for downstream specific energy as well, and our downstream energy specific energy is 5.82 feet. And we can compute the friction slope SE at each section using the Manning's equation. So our Manning equation will be this: NB squared divided by 2.22 times RH 4 by 3. So this equation comes from the equation 6.27b from book. So for that, since we already know the V, so we don't know the RH. We can compute weighted perimeter for each section, and for upstream section, so let us compute the weighted perimeter. So weighted perimeter will be like A by P. So before we compute hydraulic radius R, we need to compute weighted perimeter. So weighted perimeter for a rectangle channel will be B plus Y1. So that gives us 19 feet, and hydraulic radius will be 2.368 feet. And so when we put all these like R value, we know the N Mannington and B1 we already computed in the above section. So when we input all those things, we get the specific, no, specific. Friction slope at upstream will be 0.00365, and similarly for downstream as well, I did the same process and I obtained friction slope SE2 or SE downstream at 0.00325. So now next step will be the finding the distance between 4.7 feet depth and 4.5 feet depth. For that, there is a standard formula. This del X is equal to specific energy in downstream minus specific energy at upstream divided by S naught. This is slope, and SE, whereas SE is average of friction slope SE1 and SE2. So that is 0.00345. And when we input all those values, see the final outcome, that is del X is equal to minus 54.5 feet. The negative sign tell us the distance is upstream, exactly what we expected for Ammon curve. So there is also another approach for finding the distance. So that is called standard step method. I think we will conduct the lab for this part in the next coming week as well. So here this is the same thing, but we will do incrementally. We march from the depth of y, that is 4.5 to 4.7 in the small steps of 0.02 feet, computing del x at each increment and summing them up, and the result from spreadsheet table gives us the total distance of about minus 60 feet upstream. So the small difference from direct step result is just due to step size. The standard step is more accurate. So both approaches are fine, and you can choose any one method for solving these kind of problems. So now let's go to problem two, that deals about the Culvert design. And so it asks us to design a round concrete culvert system that can carry 300 CFS. The entrance square is with head walls and maximum headwater depth of 7 feet and maximum diameter of 48 inches as well. The culvert is 400 feet long, slope is 2%, and there is no tailwater. So we can design the culvert using the nomograph. So nomograph is essentially a graphical calculator, and before computer existed, engineers couldn't just punch numbers into the software, so they needed a fast, accurate way to solve complex equations by hand. So hydraulic engineers at Bureau of Public Roads developed this chart, and they are still the standard reference today, published in FHWA Hydraulic Design Series number 5. And so this chart B is specifically for a round concrete pipe under the inlet control, meaning the culvert capacity is being limited at entrance, not along its length. So what does that inlet control mean? So let me briefly explain inlet versus outlet control, because this is critical. Inlet control happens when water backs up at the entrance culvert. The pipe actually carry more water, but the opening itself is the bottleneck. Think of it like a funnel. You can pour water fast, but the narrow neck limits how much gets through. And outlet control is when the downstream condition, that is tailwater depth or pipe friction, are what limit flow. In our problem, we are told there is no headwater, so our controlling condition is at inlet. So that's why we will be using chart one, that is an inlet control nomograph. And this chart has three vertical scales, like this first vertical line, it indicates for diameter of vertical D in inches, whereas this line indicates as discharge, and this first line indicates the headwater depth in diameter, that is headwater divided by D. So we will be using this line first because our entrance type is square edge with head wall. And question asks already about the diameter is 48 inch. So our maximum diameter will be 48. 48, and if we assume if our given diameter is 48 and our given q is 300. So if we draw the line through this 48 and 300, it will be off the chart. So we will not go with one barrel here. So let us do for two barrel, that is we have 300 CFS, and if we need to have installed two barrel, then it will be around 150. So at the same diameter at 150 discharge, it will give us around 2.1, and which will give us around as W headwater as 8.4, that is greater than 7 feet. And so let us use 3 barrel, that is Q divided by 3, so that give us 100. So this will be our 48 diameter, and when we draw a horizontal line with this 48 and 100, it will give us around 1.3. So that will give us 5.2 feet, so which is also less than 5 feet. And let us decrease the diameter. So let us include as 42 inch. So what it gives. So when we decrease the diameter to 42 inch and same number of barrel, that is 100 Q, and it will give around 2. So when we use that value as 2, so it will give as 7 feet. So this will be okay, and our design works. And now let us go through the second steps. So, which I already talked about this, all these things like governing equation. So it is inlet governing equation, and we will have this equation. It is from the I already talked about this as well. So it is from the Federal Highway Engineers, and so for the first trial, let us took two barrels at 48 inches, that is 4 feet. Our diameter is 4 feet and our radius will be 2 feet. So flow per barrel Q is equal to 150 CFS, and our area will be pi r square. So that gives us 12.57 feet square. So when we rearrange and put the values in above equation, we will have SW as 8.31. So this design fails. We need more capacity. So for trial 2, let us take 3 barrels at 42 inch, and our flow per barrel will be 100 CFS, and plugging in we will get SW as 6.61 feet, which is less than 7 feet. This oaks, and our final design will look like headwater depth as 6.61 feet, and minimum culvert diameter will be 42 inches, and our system layout will be 3 barrel system. And now let's jump into question number 3. It asks us to design the most efficient non-erodible channel for 1000 CFS trapezoidal shape, side slope of Z is equal to 2 feet out of 1 foot vertical. So, and the bending coefficient N is equal to 0.017, and our minimum velocity as 2.5 feet per second, and our slope of ground is given as 0.0015. So I have already written the given parameters here, and we can compute the section factor from here, like area times height radius 2 by 3. So it is just the Manning's and coefficient formula. So when we rearrange these things, we get like area times r to the power 2 by 3. So that gives us value of 295. So why I did this early, because we can compute, it help us to compute the uh, value for b and y later. So let us write the equation for finding the area and hydraulic radius. So for trapezoidal channel with Z is equal to 2, Our area is given by b plus 2y times y, whereas our hydraulic radius is given by b plus 2y times y divided by b plus 2y root under 1 plus z square. And we need to apply the best hydraulic section criteria. It is the cross section that carries the most flow for the least weighted perimeter, essentially the most efficient shape for a trapezoid. This means B is equal to 2y root under 1 plus z square minus zy. So with our value of z is equal to 2, this gives us 0.47 or narrow deep channel. And when we solve this AR 2 by 3 is equal to 295, we will have Y at 7.15 feet. And our uh, B will be as 3.36 feet. So let us also check velocity. So before we check velocity, we need to compute the area. So area will be 126 feet square. So our velocity is equal to 7.9, which is greater than 2.5. And let us also check the Froude number. So our Froude number will be as 0.7. So this is subcritical. Since our flow depth we designed for y is equal to 7.15, but in real life you never build a channel wall that's exactly at the water surface because flood can happen, waves can happen, and any slight source will overtop your channel. So that's where we build the freeboard. It is the extra height added above the designed water surface to act as a safety buffer. Think of it like a rim of cup extending above the water. You want some margin so it doesn't spill. For a non-erodible line channel carrying 1000 CFS at a depth of 7.15, we use a freeboard chart. From that freeboard chart, so from that chart, our lining height will be used as 1.3 feet. This is how much the lining material that is like concrete, riprap, etc. extend above the water surface on the channel wall, and our bank wall will be used at 3.2. This is the total height of the earthen bank above the water surface, which is higher because the bank itself must contain the lining plus extra safety. So our total channel depth from the bottom will be total depth will be like y plus bank freeboard, that is 7.15 plus 3.2, so it will be like 10.35 feet. All right, so let us go through the question number 4. It is similar like question number 3, but we need to do it for erodible channel. So since this is the erodible channel, not concrete, not rigid, the design velocity should be controlled. And fine gravel has a maximum permissible velocity as 2.5 feet per second. So go faster than that and the water starts dragging the gravel away, eroding the channel walls and bottom. And we also have other parameters like Q as 1000 CFS, side slope as 2:1, and ground slope as S is equal to 0.0015. And we also make this initial assumption of Y is less than 3 feet or shallow channel is expected, and we will verify that later at the end. So let us find the hydraulic radius R from the Manning's equation. So we know velocity must be equal to Bmax, that is 2.5, not more, not less. So we plug that directly into the uh, Manning's velocity equation. So from this Manning's velocity equation, so we get like a value of R as 0.807. And then since we have already computed this hydraulic radius, and we can compute area as well, since we know the Q and we are given the Bmax, that is 2.5. So From that we have area as 400 feet square, and for perimeter it will be A by R. So since we just computed R, and our weighted perimeter will be 495 feet. And now let us set up the two equation for a trapezoid channel. We have two geometry equation, that is one is from area and another one is from weighted perimeter. So our weighted area equation is given as b plus 2y times y, whereas weighted perimeter is given as b plus 2y root under 1 plus z square. That is weighted perimeter, and we already know this 495 or 496. And then ignore some of my this calculation here. So just rearrange the weighted parameter in the form of b, so we can put the value of b in the equation 1 to compute the y. So I just rearrange the equation and make in the format of quadratic equation, like y square minus 201 y plus 162 is equal to 0. So on solving from the calculator, I get like two values for y, that is y1 is equal to 200 and y2 is equal to 0.81. So choosing the right route, that is we have two solution, and let us like verify like y, if we choose y is equal to 200, our b will be equal to minus 398, and that is not physically possible. So we will be rejecting that, and we can choose next one, that is y2 as 0.81. So that give us b width of b as 492.4 feet, which is positive and real. So our channel is channel uh, depth is 1 feet deep, and B is 492 feet wide. And also notice one thing, we assume y is less than 3 feet, and that is verified because our y is equal to just 0.81. And let us also check a Froude number. So for computing the Froude number, we need the hydraulic depth computation, and then which is equal to area by T. So it is top width. So that gives us like a 0.8. So our Froude number is 0.49, and which is super subcritical flow, and the channel is hydrologically stable. And for freeboard final step, that is bank freeboard. So we choose bank at like 3.2 feet. So total bank height from the channel bottom will be y plus freeboard, that is 3.2, that is 0.81 plus 3.2 will be around 4 feet. And here there is no lining freeboard, because erodible gravel channels have no rigid lining above the water line. The bank freeboard is the only safety margin, and it is read directly from the standard chart based on the charts. So our final summary, or final summary sketch description will be, our bottom width will be equal to 492 feet, and our water depth will be 0.81, and side slope is 2:1b. Bank height above water surface will be 3.2 feet, and total depth of bank from the bottom is 4.2, around 4. So, and that wraps up all our four problems. So let's recap some of the big ideas. In problem one, gradually varied flow uses energy equation and Manning slopes to find distance between two depths. In problem two, culvert design is a trial and error process constrained by the headwater depth and diameter. And in problem three, we use the best hydraulic section that minimizes perimeter for a given area, and always use best hydraulic section formula. And in problem 4, we deal with erodible channel, that must keep velocity below their permissible limit, leading to wide, shallow design. And freeboard, always add it. It's your safety net.